Hi everyone, in this video we are going to be finding this sum right here. This is a problem from the AIME in 2007, so if you want to read more about it, I'll leave a link in the description. Okay, so I have rewritten our problem here and I just set S to be equal to the sum that we are trying to find. So notice that we are working with floor and ceiling functions. So we probably will have to split these up into different cases. One case will be that log base square root of 2 of k, which is just this expression inside these floor and ceiling functions. The case 1 is that that is an integer, and case 2 is that that expression is not an integer. So these are our two cases here. And to help us now, let's define the set A to be all k from 1 through 1000, because up here our summation is from 1 through 1000. Such that log base square root of 2 of k is an integer. So this will help us with both cases. Now let's work on case 1. Case 1 is that log base square root of 2 of k is an integer. So what happens if that expression does end up to be an integer? Well, let's do some analysis of what the floor and ceiling of an integer looks like. Let's say x is an integer, just some arbitrary x. The floor, the ceiling of x, is going to be equal to the floor of x, which is equal to x. This should make mathematical sense. So this is very helpful because if we know that these are equal to each other, well, the inside expression is just going to be 0. So we're summing up a bunch of zeros. So to write that, we're summing all the k in the set A for log base square root of 2 of k minus log base square root of 2 of k. I've got rid of the ceiling and floor functions because we know that they are equal in this case specifically. The inside over here is 0, as we mentioned before. So this whole sum is just 0. Now let's work on case 2. And this is when log base square root of 2 of k is not an integer, so the opposite of what case 1 was. Now let's again do some analysis on what the floor and ceiling functions will look like here. So now I'm going to define y to be a number that is not an integer, meaning that it has some decimal part. Well, it should be clear that the ceiling of y minus the floor of y is equal to 1. And just to give us a sanity check, you can plug in some random number with a decimal part like 3.1. The ceiling of that minus the floor of 3.1, that's just 4 minus 3, right? So that should equal to 1. This is just a sanity check for us. Now that we know this, let's actually write the summation for this. This will be the sum of k that is not in A, because remember our set of A is when it is an integer. The sum of all the k that is not in A of k times 1. And it's 1, remember, because as we discussed, the ceiling minus the floor will be equal to 1. So as you can see, this seems to be just the normal sum of k numbers. But how do we actually figure out what the sum is? We are going to ignore the set A right now, and we're just going to sum from k to 1000 of just k. And then what we can do is we can subtract this sum over here from that, and that will give us the sum that we are looking for. So this sum over here is easy to find. That's just the sum of an arithmetic sequence. This should come out to 1001 times 500. Now clearly we have overcounted here, so we need to subtract out this sum over here. So now let's figure out what the sum on the left is equal to. Remember that the case 1 is when log base square root of 2 of k is an integer. For what k will it be an integer? Well, think back to what the definition of a logarithm actually is. If this whole thing is an integer, that means for some n that is an integer, square root of 2 to the n is going to be equal to k. Remember that n is an integer because log base square root of 2 of k is an integer. Now, what is the highest power of 2 that is underneath 1000? Because up here we have the maximum that k is summing up to is 1000. If you note that 2 to the 10th is 1024, we can see that that is right above 1000, so the highest power of 2 underneath 1000 will be 2 to the 9th. So our sum is now the sum of powers of 2 all the way to 2 to the 9th. Because k can take on either values of 2 to the 0, 2 to the 1th, 2 squared, and so on. So we can see very clearly that our sum over here, I'm going to set this to be S sub A. That is just going to be the sum of a geometric sequence, a finite geometric sequence. If you apply the sum of a geometric sequence formula for a finite sequence, you will get the sum to be 1023. And we will just subtract that from our S of t. So S of t minus SA equals to 1001 times 500 minus 1023. Now, in the original problem on the AIME 2007, it said to find this answer mod 1000, but for our problem, we're going to find the actual sum, which is not that hard to find because we can easily expand this out. And if you expand it out, you'll get 499,477. So the answer to the original problem on the AIME would be 477, but in our modified problem, this is the answer. Thank you so much for watching. Please like, share, and subscribe.